So let's continue our journey and eventually in detail the word embeddings I was talking about so much in previous sessions. Since we talk about word embeddings, let me say the approaches I was introducing earlier, they are geared to a document level analysis. We started from the document term matrix that would represent documents as vectors of word counts. So it's really geared toward document level analysis. You can classify documents, you can do sentiment analysis. Very often this is exactly what you want to do, analyzing a document, but maybe you want to do more. Especially considering NLP tasks that you perform to prepare for subsequent analysis are typically not supported by an analysis that focuses on the document level. So in the following, we will focus on individual words and learn about ways to represent words of vectors. And then, roughly speaking, we could make the point that if you can carry out some analysis at the word level, you can do everything that you can do on a document level, but also some more. A document, after all, is a composition of words, because text has a hierarchical structure. So in the reminder, we look at words. And a word embedding, basically trying to define the term, you can think of it just as a set of language modeling techniques that map words to numbers, more specifically to vectors. Embedding is equivalent to mapping. Please take that with a grain of salt. Word embedding, we will start at embedding words. It turns out, though, that the approaches that we use generalize, and that you could, in fact, also embed sentences or entire documents, or you could go to a more granular perspective and try to embed subwords or even individual characters and then map these to words. And interestingly, nowadays we see some applications of these methods for word embedding in entirely different contexts. Recently, a PhD of my colleague from marketing, he wrote a great paper on using embeddings of products in a shopping basket to understand the relationship between different products in a shopping basket. So there are more applications than just word embedding, but we should start with word embeddings. And traditionally, we represent words by discrete symbols or as one-hot vectors. That's the traditional NLP perspective. And you see two one-hot vectors here, hotel and motel. And the example is to stress right away a fundamental shortcoming of this one-hot encoding, namely that the two terms, hotel and motel, if we encode them as one-hot vectors, where we have as many elements as we have words in our vocabulary, and for every unique word in the vocabulary, there is one element in the one-hot vector that is 1, and all the other elements are 0. That's just a dummy coding of words. It's like a categorical variable that has as many levels as you have words in your vocabulary, and you encode this category variable using dummies. That's a way to look at it from the perspective of my winter lecture, Business Analytics and Data Science, where we did just that. And then, if you follow this approach, two words will, in their vector representation, they will always be orthogonal to one another. And that's the lower equation here, where we look at the cosine of the vector between the two word vectors, between our two one-hot coded word vectors. You can show, or it turns out that this is always 0 because the two vectors are orthogonal. If you want, you can convince yourself using this little Python script, but well, actually we could quickly make that point. It's fairly easy. If you imagine that a vector, essentially just a bunch of numbers, you can interpret a vector of some dimension as a line from the origin of your space to that point. So let's say we have two dimensions. This is x1 and this is x2. So our vectors are u and v we assume they live in R2. And then u is just maybe 3 for x1 and maybe 5 for x2. That might be here. So that is u. And same for v. We also have v at some point in that space. Maybe v is somewhere here. And then the angle between them, this angle or the cosine of it, let's call that theta. Cosine of theta you can work out using this equation. That's just a bunch of linear algebra we are using here. And this measure is used a lot, turns out it's used a lot in text analysis, where we think of it as the cosine similarity between two word vectors. The larger this angle, the more dissimilar two word vectors are, and the smaller that angle, the more similar they are. That's just a way to measure similarity. In fact, in business analytics, we use the cosine similarity as well, or at least we introduced it in the scope of clustering algorithm. That also needs ways to measure similarity, right? So that's a quite well-established concept, measuring vector similarity by the cosine of the angle between them. You see the calculations. Now, the thing is, if we encode our vectors as one-hot vectors, then, well, they will look like this. One element will be 1. So here is 1. And the other element will be 0 by definition in a two-dimensional space. So that is my v. And then let's say this is my u. And here would I have a value of 1. Just to make that look a little nicer. Should use the same colors, right? This is u and the other is v, and this is u. Sorry for my handwriting. And the angle between them here, now it's 90 degrees, meaning that the cosine between them turns out to be 0. And this is what we had before, right? This is what I was saying. If you have one-hot encoded vectors and you look at their similarity, by the design of your encoding, by your design of how vector words are represented as vectors, all the word vectors are orthogonal, and you cannot work out the distances between word vectors. Which is bad because the two words in this example, hotel and motel, they do share similarities. They express a similar concept. Not exactly the same, but the concept is similar. And it does not make much sense that the distance between the two words hotel and motel is exactly the same as, for example, the distance between the word hotel and river. So if we, just for fun, add the word river to our picture here, let's do so. River It also gets encoded by means of a 10-dimensional vector. In my example, I'm using a vector with 10 elements, which implicitly means that my vocabulary has only 10 words. In practice, these vectors would be a lot bigger, but 0, 0, 0, 0, 0, 0, 0, 0, and one more, 0, 0. That's our 10-dimensional vector with all zeros, and the one-hot encoding of river could be that we have maybe, it's the last word, one single item, one single element, which is 1. That would be the word river. And then if you do the calculations of the similarity between the words we have here, hotel, motel, and river, using the cosine similarity, they are all 0. So from a similarity perspective, from the perspective of vector similarity, there is no way to distinguish whether the word hotel and river are any more similar than the word hotel or motel, or whether the word hotel and motel are more similar than, for example, motel and river. For all pairs of words that you could imagine, the cosine similarity is always the same, it's always zeros, all our word vectors are orthogonal. And maybe just intuitively, just by gut feeling, you agree that this is not nice. This is not really what we would like to have when we represent words as vectors. We are talking about words. We represent them as vectors because vectors we can process with our learning algorithms, but we would our vectors like to behave as words behave, or to exhibit the properties of the words that they are meant to encode. And as a matter of fact, it turns out that you can look at that a bit more formally and state that any embedding, any good embedding, should respect distributional semantics. That's a big word. Distributional semantics. What's that about? Well, in a nutshell, there is much research being done on linguistic and how language develops, and then there is computer linguistics. Anyways, we have a rich set of theories and methods available that are concerned with quantifying the semantic similarity between linguistic items, which in our case are words. Methods to quantify, so to measure the semantic similarity between words, how similar two words are, whether they refer to similar concepts like the words hotel and motel. And this quantification works on the basis of the distributional properties of these linguistic items in large samples of language data. So that translates into you build up a big corpus of text, and then you focus on the distributional properties of words in that text. And the belief is that the meaning of a word is given by, or at least approximated by, words that frequently appear close by to that word. Or, put more bluntly, you shall know a word by the company it keeps. And an important element for the task of word embedding that comes from this theory is the distributional hypothesis. And if we manage to design a word embedding in such a way that it obeys this hypothesis, we sort of have grounded our word embedding or our embedding method in this theory, which obviously is nice to have, is a good thing. So what is the distributional hypothesis? It states that the more semantically similar two words are, think about hotel and motel, semantically rather similar, the more distributionally similar they are. So if we analyze a large sample of language data and examine the distributional properties of the words hotel and motel, how often they occur, for example, then we would basically find that the distributional properties that are similar between the two words, they are similar. That's what the hypothesis predicts. The more semantically similar two words are, hotel, motel are semantically similar, the more distributionally similar they are. So they should exhibit similar distributional properties if we analyze this large bunch of text. That's the prediction of the distributional hypothesis. And then it goes on, if they are similar in distribution, then it is more likely that they occur in similar context, which makes sense. If I'm looking for a place to sleep overnight, if that is the context, I'm now looking for a place to sleep, hotel and motel clearly occur in that context. Both of them occur in that context. And now the question is, okay, we have this hypothesis. We could also look at it as a design guideline. We would like to design our word embedding such that it fulfills this hypothesis, and the more they will tend to occur in similar context, our distributionally similar words, the more they will tend to occur in similar context. This hints at the co-occurrence counts between words being a good starting point to design our embedding. And this matrix looks much like the one we've covered in the previous chapter, but note the differences. This is not the document term matrix anymore. Traditionally, we paid much attention to the document term matrix to carry out document level analysis. And now we don't carry out document level analysis. Our interest is word level analysis. And our starting point here to construct an embedding could be, according to the theory, the word co-occurrence matrix. Words that are semantically similar, this is what the theory predicts, co-occur or occur in similar context. And this word co-occurrence matrix, you can guess that this matrix in practice is very big because it is word by word. It's whatever size our vocabulary has. Let's say it's 30,000 words, then this matrix has dimension 30,000 by 30,000. So it's a fairly big matrix of word co-occurrences. And we can construct that matrix by processing a large bunch of text data. Now, if we have this word co-occurrence matrix, we can probably use some linear algebra in order to process this matrix or to work with this matrix. And that's the idea of modern embedding techniques, I would say. So we collect distributional information in high-dimensional vectors in our embeddings. They should resemble this distributional information. And we define distributional similarity as vector similarity, which we can measure using, for instance, cosine similarity. Similarity between vectors we can measure easily, and we define vector similarity to be the same as distributional similarity, which we understand as semantic similarity. So if we achieve an embedding where, unlike with the one-hot embedding, semantically similar words are close to one another, then we have a nice theory support for our embedding. And afterwards, if we collect this distributional information in high-dimensional vector, going from this word co-occurrence matrix, we can use dimensionality reduction techniques in order to make this matrix more handy, more processable. And as a matter of fact, LSA and LDA, you can really look at them from this perspective, applying dimensionality reduction to the word co-occurrence matrices, whereby LSA focus not really on word co-occurrence but on the co-occurrence of terms. Remember, the focus of LSA was to address the problem of the back of word model to capture synonyms, to deal with synonymity in language, which the vanilla back of words model was unable to accommodate. That was the goal of LSA, and to achieve that we used matrix factorization to then afterwards reduce the dimensionality of the factorized matrices, we denote them by U and V, these document concept and term concept matrices. And it's a bit similar with LDA, where we also focus on similarity, but it's the topical similarity that's key to LDA. But it's both techniques, that's the key take home here, both techniques emphasize the importance of similarity. Paradigmatic in the case of LSA and topical in LDA. This is how we could refer to that. And next we introduce a neural network based way to construct the word vectors, which also ground on this notion of similarity. And with this little detour into the space of distributional semantics, you got an idea why the similarity between our word vectors, our word embeddings, is so important. Alright, so what neural networks do when they embed words as vectors is they construct a distributed representation of the words. That's yet another term, big term, I know, distributed representation of words. What is that again? Well, actually, it's nothing but a dense vector, as opposed to a sparse vector. Remember, one-hot encoding leads to very sparse word vectors. Neural networks construct dense word vectors. Statistical approaches, LSA, LDA, they have inbuilt dimensionality reduction capabilities to start with from this big co-occurrence matrix of the words and then cook it down using dimensionality reduction. And here in the neural network oriented techniques, we start from a lower dimensional space right away and aim for this distributed representation. And that's really key in this feature learning capability of deep learning. When you hear deep learning promises to learn features automatically, it has much to do with these distributed representations that neural networks derive as part of their training. And it has to do with the way they encode information in hidden layers. And remember that many neural layers, that many neural networks have this type of funnel structure, where the number of neurons decreases layer by layer. That's not true for all neural networks, but we often see that. And that's a way of condensing and distilling information, enriching it, making it more precise. So to understand what a distributed representation is, it is a good exercise, I believe, to start from the opposite, from a local representation. And I have this little animation which hopefully you will like. Actually, my son likes it a lot because he's a big fan of toys. Of cars, sorry. Of toys as well. Anyway, cars. I think the last movie I had to watch was Toy Story. This is why I said toys, but in fact. My example is from cars. So here we have Guido. Sorry, we have Luigi. Oh, I'm so rubbish. We have Luigi here. And let us assume we are trying to find an encoding, a way to encode the information that we see here, which could be a binary variable, which the two states we see a small yellow field, 1 or 0, we don't see a small yellow field. That is a local representation of the concept of this little small yellow field. And the point is that if we encode information in this very local manner, what if we observe a new concept? Here's Guido. So now we need to grow our representation of the concepts that we try to encode. And we could do it here using 2 bits, where then we have 2 states, 1 is 0, small yellow field, or 0, 1, small blue palette check. Okay, and the more and more concepts we encounter, the more complicated or the longer gets our encoding. Here, for instance, And this is why it is a very local representation that I'm showcasing here, which is to be distinguished from a distributed representation. Distributed means that the different bits in my codes sort of collaborate with one another. Here they don't. The first bit encodes the concept small yellow field or not, and the second bit encodes whether the concept is a small blue pallet jack or not. But the two bits do not sort of collaborate. And because of that, I couldn't encode, or I could not represent the concept bumblebee with that code, because it's a local representation. And if we change that, if we make it a distributed representation, then we could come up with this solution here. We do need 3 bits now still, but this representation of the different concepts that we are seeing, these cars here, we could engineer it such that the first bit represents whether something is yellow, the second bit represents whether something is small, and the last bit represents whether something is transformable. An ability only Bumblebee shows. And the point I'm trying to make here is that here the entire concept, we represent it in a distributed manner. We have parts of it representing the color, because we identify color to be important. Other parts of my encoding represent size, because we see size as something being important. And then we have this ability to transform oneself, which is yet another part of my code. And with that code, I could even represent concepts that I haven't seen before, because there is flexibility in my code. It's distributed. I could also represent omnibus prime, for example, as not yellow, neither small, but transformable. That's the essence, with a smile, of distributed representations. And the key question, however, is, okay, that makes sense. The representation here is yellow, is small, is transformable, is better, makes more sense, is more flexible compared to the previous example where I had 1 bit for Luigi or not Luigi, another bit for Guido or not Guido, yet 1 more bit I would have needed for Bumblebee or not Bumblebee, and then I would have needed another bit for is Optimus Prime or is not Optimus Prime. That's really inefficient if we face many concepts. So you certainly agree, my interpretation of the 3 bits of my code here is yellow, is small, is transformable, makes a lot more sense. And then the question is, how can we learn a good distributed representations? How do we know that is yellow, is small, is transformable are the right interpretations of the places in our code? That's certainly a difficult question. Fortunately for us, scholars have found good answers to these questions, and many methods have been proposed to learn distributed representations for words that capture meaning. And well, the list is quite big, I have to say. Clearly some very prominent examples include Google's Word2Vec and Stanford's Groovy and Fast Text, which goes back to Facebook. And then there is Gensum also, which is a tool. It's actually a Python library for topic modeling that's used a lot and became quite popular and offers some word embeddings. And I have highlighted one word here. There are several approaches that make available pre-trained embedding. And this pre-trained obviously looks very important due to the red color, and in fact it is very important. So before detailing that pre-training thing, first of all, let's note all of these approaches, and we will look at Word2Vec because it was the first one to come out, but they share many similarities. They all create a low-dimensional representation of words as real vectors. And by low, I mean relatively low, and the reason that our embedding can be relatively low is because it's a distributed representation. Therefore, it can be lower compared to, for example, one-hot vectors, where we would need 1 bit for each word in the vocabulary. I forgot to stress that. It's important. In the example with the bumblebee and Optimus Prime, right? Please note that the starting point, this local representation, was actually equivalent to the way we encode words when using this one-hot approach, right? And this is how to interpret the low here, low-dimensional representation. We have a distributed representation, and therefore we need less dimensions compared to one-hot. And conceptually, you could draw some similarities or identify similarities to LSA, but we organize the calculations using neural networks, which we train on large corpora. And what comes out are these embedding vectors, which basically equate a word to a bunch of numbers. This works like a hash table. And therefore, we can use pre-trained embeddings that Stanford and Google and Facebook and others have trained for us, made available, and use these embeddings to represent the words we have in our data, which I believe is quite interesting. So let's examine that in some more detail. And before looking at any formulas, I want to introduce you to the probably most famous example of neural word embeddings, and Word2Vec in particular. They learned word vectors, and what made these techniques very famous, well, I believe these examples that you see here contributed substantially to their popularity. The vectors that you obtain from this neural word embeddings show some very interesting characteristics. In particular, this example is very famous. You have 4 word vectors: king, man, queen, and woman. And as we have seen in the example with the cosine similarity, a vector that's basically a point in a multidimensional space, we can draw it in like that. And if you then subtract from the word vector of king the word vector of man and add that of woman, the result that you obtain is a vector that looks very much like the word vector of queen. King means minus man plus woman equals to queen. Word2Vec word vectors exhibit such behavior that numerical calculations resemble semantic relationships. That's one famous example. There is another one concerning cities and countries. That's this one here, where you can basically show that the relationship between the word vector of China and the word vector of Beijing is similar to that of Russia and Moscow, or Germany and Berlin. This is another form of a semantic relationship that the resulting word vectors exhibit. And that's quite interesting, I believe, and it shows that in the way scholars at Google constructed these word vectors, they have really picked up some semantic relationship that exists in human language, because otherwise you would not see such behavior, how calculations, algebraic calculations, resemble concepts that exist in language. So let's sketch the idea of Word2Vec, which is very similar and will feel quite familiar, I believe. In fact, what you do, you use a neural network to solve a fake prediction task. Well, why a fake task? Fake is just saying that you artificially construct a prediction task because neural networks do well with prediction tasks. You can train them nicely, minimizing empirical loss, all that works well. And if you want to train a neural network, good if you have a prediction task. So Word2Vec constructs one. We start from a corpus of text where we in fact do represent words in our fixed vocabulary using one-hot vectors for start. So let's consider the sentence, "Stop talking, lecture has started." I wonder how I came up with this example. Nowadays, however, well, nobody's talking. I don't like that any better. Anyways, stop talking, lecture has started. And there are two versions of Word2Vec. One is called continuous back of words, the other is called skipgram. They are somewhat similar, same, but different. Let's say the word lecture is our focus word. You see the one hot vector of lecture, or you actually see the full encoding for all the words in that little sentence here, exemplified. And let's say we are interested in the word lecture, make that our focus word, and we can construct a fake prediction task in which we forecast the occurrence of the word lecture given the context "stop talking has started." You see my point? This is what I mean by fake prediction task. We just partition the words that we have in a sequence of text into context word and target word, or target words. And then we're trying to predict the target word using the context. It's very similar to this idea, know a word by the company it keeps. We believe that the context word will trigger the occurrence of target words, of other words. So we construct this prediction task considering neighboring words. And for simplicity, let's start with an example where we consider a context of only a single word, of one word. With this context window of just one word, we can write down all the training examples that result from the sentence "stop talking, lecture has started." And if I'm using blue for the input or context word and purple for my target word, then I could have the first tuple, stop, and talking, whereby talking is the target and stop the context word. But I could also predict it the other way around. I could say, well, why not predicting the target word stop from the context word talking? That's equally possible. And then it goes on. Next we have talking and lecture and talking. And we then shift our window forward to obtain lecture and has and lecture. Has started and started has. This gives us the last training tuple. So you see how we incrementally move our window over our text, always using a context window size of just one word, and then create this training examples where we have neighboring words, just one, simplification, but leave it for now, and predict the neighboring word. It's very similar to language modeling. Just here, it's not that we always predict the next word in a sequence. It's a bit more flexible, or well, we also predict backwards, or we just more generally predict target words from the context, whether it's the left context or the right context or both contexts. That is flexible. And this is the difference to language modeling. And this data that we now have, it's just tuples, right? And if we start from one hot vectors, then both the context word and the target word will be a one hot vector. We can represent them as one hot vectors. And then, as a matter of fact, we don't even need a deep neural network. A very shallow neural network is more than enough to approach this prediction task. Let's look at the picture. Stop talking, lecture has started. You have seen the tuples of context and target word. We have a neural network here where our input is a one-hot encoded context word with dimensionality v. V is the size of our vocabulary. We need that many dummy variables to represent every word in the vocabulary with a one-hot vector. And on the output side, we also have a layer with v units, same size as our vocabulary. As a matter of fact, the output layer is exactly as in my language modeling examples. It has one element for each word in the vocabulary. And then we will use a softmax function to ensure that our outputs, and here they are denoted by y, correspond to probabilities. So we obtain a probability distribution over words from our shallow neural network, and we interpret this output as the probability of a word y1, y2, y3 being the true output or target word given the input word. And if we I need purple. Often I use purple for actual targets. I know, untrue. Purple was my target layer. Anyways, if we imagine that we have, if we feed the word stop in here, so if this is the word stop with a 1 only at position k, and if we believe that our target word then is the word talking, maybe this is the way to represent the word talking. And in each of these units y, we have some probability. So here maybe we have 0.01, and here maybe we have 0.002. And let's say y3 we have 0.11 and so forth. Then we can nicely use cross-entropy loss in order to train this neural network, which has some hidden layer, just one hidden layer of some dimensionality of some size denoted by capital N here. The input layer and the output layer both have the same dimension, v, and the hidden layer, well, we are free to pick any dimension we want to give it. What's done in Word2Vec and similar techniques is we use a smaller hidden layer. So we would assume here that n is less, actually much less than v, our vocabulary size. Just in case, if you have ever seen an autoencoder, this architecture looks a little bit like an autoencoder in that we have this bottleneck layer here. The hidden layer is sort of a bottleneck layer. We feed all the information from the input of dimension v, and then in the hidden layer we need to condense this information. We need to reduce the dimensionality because we only have n units that are to capture the essence of our input, and then we map that back to the output dimensionality v. And we have two weight matrices here, both of which have dimensionality, well, n by v and v by n, but they have the same number of elements. And these weight matrices are what really matters in the scope of Word2Vec. Because if you think about it, what these weight matrices do, we train our neural network over a large corpus in order to calibrate these weights so that these prediction tasks are solved with high accuracy, that the neural network really is able to predict the target word from a context word, so that the neural network is getting really, really good at predicting words that, if you think about it, co-occur next to one another. In this example, window size of 1. So our neural network, if we train it long enough and have enough text data available, it will get really good at predicting neighboring words, words that often co-occur. Know a word by the company it keeps, right? That is exactly what our neural network is learning here. And then these weights that we have here, if you think about it, the input to our neural network is 1 hot. So all the x values, all the input values are 0, but one of them. And if we carry out the multiplication, if we calculate x times v with this 1 hot encoded input vector x, then only a single column of the matrix V will in fact be used. All the others are sort of erased because of the 1 hot encoding that will be used for X. Does that make sense? I hope it does. Well, otherwise convince yourself, maybe doing a little toy example in Excel, that this is exactly what is happening here if we do the multiplication with this 1 hot vector x. And so the activation of the hidden layer, that's basically one column in our weight matrix W. And I haven't said that, but in Word2Vec we do not use any nonlinear activation function. So arguably it's not even a neural network that we are using here. And this matrix W is, because of this design, is something like a lookup table. We feed it a 1 hot vector, and this 1 hot vector, depending on which one we'll feed, it always represents one word, and then we sort of extract with this matrix multiplication one column from our matrix W, from this weight matrix. And that essentially means that the output we get certainly is an n-dimensional vector, and that's the word embedding. So the matrix W is the embedding matrix. We call that the embedding matrix, and all these elements that we find in W, all the columns of W, these vectors of dimension n, they represent the word, the input word, whatever it is. They represent this input word. So this is the embedding matrix. Setting up this neural network, we get an embedding matrix from which we can basically pull just the individual column, each of which represents a word. It functions exactly like a lookup table. We put in a word and we get its embedding of dimension n, capital N. Just that we don't do a normal lookup as in database systems or something. We do a lookup by means of matrix multiplication using a 1 hot encoded input vector, which results effectively in a lookup because we extract just one column. Maybe I should write xt here because x, by the way this graph is constructed, looks a bit more like a column vector. So that is essentially what Word2Vec is about, whereby we still carry along this simplification that we predict only neighboring words. And you could guess, I believe, that that cannot be too powerful, because the words that co-occur together in a sentence, are they necessarily semantically related? At least they will also have relationship in a syntactic sense. An article followed by a noun, right? So looking only at the neighboring words, that is probably not powerful enough. And indeed, Word2Vec does not use an input or a context window of size 1. It uses a bigger context window, and then we need to generalize our architecture a little bit. But now that we have seen and experienced the architecture, that should not be a big problem for us. So let's generalize Word2Vec to larger context using more than one word. And at this point, the difference between the two flavors of Word2Vec, SIBO and skipgram, will come into play. We keep our sentence, stop talking, lecture has started. And let's say lecture is our target word. And now we have a window of two words, a context windows of two words to the left and two words to the right. And then our input data would have the form of stop and talking and has and started, and the output would still be lecture. This approach, this flavor of Word2Vec is more intuitive in my opinion, and that is the SIBO approach, the continuous back of words. So the architecture of our neural network also has changed a little bit, but only a little bit. We still have this n-dimensional hidden layer, and we still have the v-dimensional output layer. And that makes sense because SIBO predicts one target word from a surrounding context. And how large this surrounding context is, that's a meta parameter. That is something one can decide on. In this example, the context window is 4 in total. And in the picture, we have 3 inputs, and then we have the little dots here to exemplify that we could have many more depending on our window size. So the input layer of our neural network basically has V times whatever is the number of context words units. One of these pillars would be the word stop. And the next pillar would be the word talking. And the next pillar would be the word has. And all of these words, and now I would also need started, but my picture is not that big. So please imagine that there is a fourth pillar which would represent the word started. And each of these words is one hot. So I have 4 by V input units in my layer. And then what you also see here is that, well, in a vanilla neural network, feed-forward neural network, we would then have a matrix which is W by 4 V times N. So the number of weights grows a little bit, but we could use parameter sharing so that we have, and this is shown in the picture here, always the same weights for each of the input words. And then everything is exactly as it is before. So that is SIBO. How about skipgram? Well, that's the other way around. Here we basically just exchange the two sides. We predict the context words given a center word. Our input is now a v-dimensional vector of one word, which is the focus word. And again, we design a context window of n words to the left and to the right. And we then construct our training data, which, if we assume a window size of 2, could look as shown here. For method, we have the target words and efficient for learning. For the focus word for, we have efficient method, high quality. And for high, we've got for learning, quality, and distributed. And it continues like that. In a nutshell, we can again construct our training data, and we can come up with a neural network architecture, which the structure of which you see here, where we have these stacked pillars representing the multiple context words using a one-hot encoding. So the output layer has the dimensionality c by v. Now, whereas the input layer has dimensionality 1 by v, we have this bottleneck layer again. And we basically construct our forecast, we construct a probability distribution over c words, c being the number of context words. And then we again train this network using cross entropy, right? Because we could easily plot or add the actual targets to this picture, which are just one-hot vectors. And then whatever probability distribution we get from our neural network, we can compare that to the actual one-hot vector of the word we were looking for, and then backpropagate the error to train the weights. That's the idea of Word2Vec. And you could ask, okay, in skipgram, so how do I then get the word vectors? And as a matter of fact, Word2Vec learns two representations of a word by design, because you have these two matrices, W and W prime, both of which have this dimensionality, hidden layer size times the vocabulary. And therefore, in both of these matrices, W and W prime, you have one column or one row giving you the embedding vector of a word, of the focus word. And in theory, you could use either of them, W or W prime. Generally, what people do use is the weight matrix near to the single word as vector representation. So for example, in SIBO, the output is a single word, and hence the weight matrix between the hidden and the output layer is preferred to, well, and we take that one as our embedding matrix. Whereas in skipgram, it's the input layer where there is the single input word, and so the weight matrix between the input layer and the hidden layer is preferred as embedding matrix. In either case, these embedding matrices, as we learned, they function just like a lookup table. And if we go into this lookup table with a one-hot encoded word vector, we can pull out the embedding of that single word that is represented by our one-hot vector. And then what we basically do when we want to make use of these embeddings, these weight matrices, you can store them. Obviously you can store them. And this is what I called pre-training earlier on. Word2Vec embeddings, meaning these weight matrices, are available for you to download. It's basically just a text file where in the first column you have words and like a CSV file, right? Comma separated value file. You have one column which is a word, and then you have many columns that represent the numerical representation of that word. And you can download these in different forms. There is one, I believe, where capital N was 50, and common choices for N are 100-dimensional word vectors, or if you have the computational capacity, you can also download 300-dimensional word vectors. And then each word in the vocabulary is represented by this 100 or 300 dimensions, numbers, essentially. And these you can download and use in your application. One issue that you need to take care of is that in your application you might see words that were not part of the vocabulary on which Word2Vec was trained. So you have out of vocab cases. That's absolutely not uncommon. Rather, it's quite a typical setting that issues like this one arise where you just lack the embedding of one of the words, and there are standard actions that you can take. And here are some applications for Word2Vec embeddings, and equally for other word embeddings as well. That's not specific to Word2Vec. That was sort of the first paper that came out and was widely recognized. I think if I put it like that, it's accurate and fair to all the other scholars that contributed to the field. This is why we started with Word2Vec. We will briefly look into some others in the next lecture. And in the matter of fact, for us who use these embeddings as consumers in downstream applications, in econ applications, for instance, it does not matter so much which one we pick. So it's important that you got the idea of how they function, and to further sharpen that understanding, we will play around with that certainly in the tutorial. Anyways, I wanted to go through some applications. So one maybe more of a toy example is this showcasing of the embeddings embodying semantic relationship, like A is to B as C is to whatever. Remember with France to Paris as Germany to Berlin example. So this is something you can do with Word2Vec and with these embeddings, or examples like king minus man plus queen equals woman. That's nice, a nice way to sell word embeddings, but it's not dramatically useful in own right, I believe. More interesting, think about machine translation. You could learn in word embedding using some corpus in your source language, say English, and then you learn in embedding using a corpus from your target language, say German. And for instance, you could use the English Wikipedia and the German Wikipedia as your corpora to train these embeddings, and you could in both cases pick the same dimensionality for the hidden layer, for the embedding layer, say 300. And then when you translate from English to German or vice versa, well, words with a similar meaning, they should be close to one another. That was the distributional hypothesis. That was our guiding principle when we designed these word embeddings, and this is our justification why it makes sense to look at target words, at context words, and create this fake prediction task. This distributional hypothesis really is the basis. So for machine translation, why not taking the word vector in the source language and then look for the closest vector using cosine similarity among the embeddings in the target language and replace one with the other. That is not going to work too well, I have to admit, because the grammatical structure of languages differs across language. So you cannot translate a sentence word by word. That is not going to work too well. The result will sound or will look like, well, a bit robotic, so to say. It would not be a good language. If you translate from English to German that way or vice versa, the quality of the result will not be very good. The overall meaning, however, that should be covered. So you shouldn't get the translation to mean something else. It's more the synthetical rules, the syntax rules of the target language that will get violated if you translate word by word. But you could imagine that you first translate word by word, and then you have sort of post-processing that takes care or tries to remedy this violation of the grammatical structures. If you have a sort of rule system, how grammar differs between English and German, or source and target language, then in fact there might be a way to remedy this. Well, it turns out you don't need to worry because there are better ways to do machine translations, as we shall see. But that could be a candidate application. Document classification and sentiment analysis is yet another. At this point, we would need a mechanism to aggregate words and word vectors to the sentence or document level, depending whether we want to predict sentiment in a sentence or the document as a whole. We could just average over the word vectors. That's a crude approach. In practice, it might not work too bad. It's quite feasible. You have a sentence, a review. You map every word in that review to its embedding. Maybe just ignoring out of vocabulary words. Then for every word you have a vector, a bunch of numbers. You average over them. And that gives you a distributed representation of your document. And then you could use a classifier, feed it with these document representations, and train it to learn polarities from labeled training documents. That does work. And to make it a little more powerful, maybe you don't do weighted, maybe you weight the word vectors in your averaging using, for example, TF, IDF weights, a bit less crude, still crude. These are just some ideas. As a matter of fact, there is a nice paper co-authored by Mikolov, who was the first author of the famous Word2Vec paper, where they proposed Doc2Vec. So same idea, just that you don't embed a word, but a full document. And these are just some examples of the things you can do with word embeddings. Nowadays, they pretty much show up in maybe not any, but many NLP tasks where you just use pre-trained embeddings as a starting point. And we shall see that in later sessions. But we do indeed leave this for later. It is time to sum up. So in this lecture, we discovered and reviewed the fundamentals of natural language processing. You have learned about the NLP pipeline and some of the standard steps that it entails. Filtering, tokenization, stemming, lemmatization, for example. I also wanted you to understand the traditional back-of-words model as well as the newer, more modern type of neural word embeddings, together with their respective pros and cons. Well, we did not mention many cons, many disadvantages for word embeddings, but we clearly identified a couple of shortcomings of the back-of-word approach. You have seen how Word2Vec allows you to create word embeddings that exhibit these distributional semantics or fulfill the distributional assumptions and this distributional hypothesis. And you have seen that, interestingly, it requires nothing more but a shallow neural network, not even one with nonlinearity, in order to train these vectors. And as homework, I would like you to further read On these word vectors and these embeddings, there is a nice blog, The Amazing Power of Word Vectors, that you'll find in the literature slides, and also a tutorial paper which gained popularity by Ron that does a very nice job, I believe, in explaining the functioning of Word2Vec. And in the next session, we want to elaborate on this functioning so that you have some more information on Word2Vec, but also get an idea how it differs from other embedding methods like Groovy and FastText. That is the scope of our next lecture. And I would once more like to express my gratitude to all the great resources that contributed materials to this session. Here I would like to draw your attention particularly to the first source, the blog of Jay Alama, who has a post called The Illustrated Word2Vec, and I would like to draw a big exclamation mark here, because this is something you definitely must read. It is a beautiful, graphically extremely appealing introduction to the functioning of Word2Vec, and a must-read in my opinion. Find some other nice papers here, and of course the standard resources I am drawing on: Dive into Deep Learning and the NLP Processing with Deep Learning course at Stanford. The sources that I was citing you find here in the literature index. And now it is time for me to say goodbye for now, and I look forward to see you in our next session. Thank you very much. Take care. Until very soon.